Hello, everyone. Welcome to Physics 213. This is Lab 3, which is on circular motion. So originally, I made a video for this lab during the pandemic, during the peak of the pandemic, where the labs are combined. So I'm going to post that video right after this one. It'll follow this. However, just be aware that the lab numbers might be slightly different. I think it was called Lab 2 or something when I combined it, or maybe even Lab 1. In this case, it's just Lab 3. It's just on circular motion. And the other thing that might be different is the numbering. So the questions should be the same, or basically the same. The only difference might be the numbering. Okay, so you can just ignore those. Make sure you go by this semester's handout for Lab 3. One other thing is, if you watch the video, you'll notice also that there's data, right, in some of these tables, because I had to pre-collect the data because students weren't able to collect data during that semester because of COVID. Okay, so I just wanted you to be aware of those slight differences. Otherwise, all the material is exactly the same. Great. So now I will continue with the information on circular motion. Thanks. Hello, everyone. Welcome to Physics 213, Lab 1. This lab is going to cover several topics. First of all, we'll talk about circular motion, which we'll look at something called a rotational apparatus, and where we calculate the centripetal force. We'll also look at a ball, like a steel marble, rolling over a roller coaster track and a loop track, where we have it set up so that the marble is just ready to leave the surface of the track at a particular point. And we're going to calculate what's called the critical speed of the ball, just when it's ready to leave the track. Then we'll talk a little bit about moment of inertia. We'll calculate the moment of inertia of an aluminum rod or aluminum stick about several different points, several different axes of rotations of that aluminum rod. And then finally, we'll look at a little bit of conservation of angular momentum, where we have a student sitting in a chair rotating, and then they are either bringing in weights, pulling weights close to their body, or they're rotating a wheel, spinning wheel. It's kind of counterintuitive. I have a video that was recorded several years ago on this, and we will watch that video and at least qualitatively talk about conservation of angular momentum. Okay, so to start, let me go over a little bit of the theory of circular motion. Okay, so I want to start by talking about what's called uniform circular motion. Let's say we have a particle and it's traveling at a constant speed. So at this instant at the top here, let's say it has a velocity vector in this direction. So this is, say, v1. And then a little time later, let's say it has a velocity in this direction. Right, the velocity vector is always going to be tangential to the path. Remember, it's traveling in a circle. And when I say it's traveling at a constant speed, it means that the magnitude of those velocities is the same, right? It's constant. So the length of v1 and v2 are always going to be equal, right? So remember, the definition for average acceleration, it's equal to change in velocity over change in time. So there's going to be an acceleration if either the magnitude of the velocity changes, right? That would be the case if you had one-dimensional motion, or the direction of the velocity changes, or both. In this case, the magnitude of the velocity is not changing, but the direction of the velocity vector is changing. So we do have an acceleration. Okay, so to figure this out, remember, I can write delta V as, it really means V final minus V initial. So in this case, I'll call it V2 minus V1, right, over delta V, or sorry, over delta T. And then V2 minus V1, I can write as V2 plus a negative v1, right? When I subtract vectors, it's the same as adding the opposite of that second vector. So what does that look like? Well, in this case, right, if I draw v2, remember v2 looks something like this. So this is v2. v1 was up here, right? So negative v1 is going to be the same length, but it's going to be in opposite direction. So if I add negative v1 to v2, then I want the tail of negative v1 to be at the tip of v2. So it looks like this. So this is really negative v1. So I'm adding here, right? So this is v2 plus negative v1. And that result is going to be delta v. That's my change in velocity. So it's in that direction. So it turns out, and it's hard to see this, I'm sort of just doing this qualitatively here, but it turns out that the direction of delta v is going to be towards the center. And since the average acceleration, right, remember, is equal to delta v over delta t, and delta t is just a scalar, it's just a number. So the direction of the acceleration depends on the direction of delta v, because that's what the vector is, right? So in this case, the acceleration is going to be towards the center. So the acceleration will be directly towards the center. Okay, and that acceleration has a name. It's called the centripetal acceleration. So this is the centripetal acceleration. So whenever a vector is changing direction, and if it's traveling in a circle, right, if it's changed direction and the path of the object is circular, then there's going to be this centripetal acceleration towards the center of the circle. Now, in lecture, you also learned that it has a magnitude, right? And that magnitude depends on the linear velocity, the tangential velocity, and the radius. So let me just give that to you now. So sometimes you write magnitude as absolute value of A, or you could just say A. I'll just write a little c here to remind you that it's centripetal acceleration. And remember from lecture, it's equal to v squared over r. Right, so that's the magnitude, but the direction is towards the center. Now, we also know how to relate the angular speed or angular velocity to the linear velocity. So if I have, say, a circle again, let me draw it here. And this is my radius. Let's say I want to know the linear or tangential velocity v, and actually I'll just look at the magnitude of it, so I'll just call it v. And I know that the angular velocity or angular speed omega is so many radians per second. Then the v here, this tangential or linear velocity, is simply equal to r times omega. Okay, so another way that we can write the magnitude of the centripetal acceleration is instead of v, instead of the linear velocity, I can plug in r omega. And if you work this out, right, this is going to be r squared omega squared over r, and one of the r's will cancel. So another way of writing the centripetal acceleration is simply going to be r omega squared. So you can either write it as v squared over r or r omega squared. In one case, it's written in terms of the linear velocity. In the other case, it's written in terms of the angular velocity or angular speed. Okay, so that brings us to centripetal force. What is the centripetal force? Well, basically, it's the force, it's the net force that causes the centripetal acceleration. Okay, so centripetal force again, it's going to be directed towards the center, right, at the circle. And the way you can think of it is it's the sum of all the forces in the radial direction. And it's equal to ma, right? But the a here is a centripetal acceleration. So I could write this as either mv squared over r. So that's one way of writing it. Or I could write it as m times r omega squared, depending on whether I want to use the linear velocity or the angular velocity. Okay, so that's an important equation. We will need to use this later in the lab. All right, the second thing I want to talk about, and this deals more with the roller coaster track and the loop track. Actually, let me go to a new page here. So let's say we have a curved surface. And we're going to assume it's circular. And in one case, we have the ball rolling on top of it, like a roller coaster. And in the second case, we have the ball rolling underneath. So that would be like the loop. And we want to know what's going on right when it's at the peak of that curve. So first of all, what are the forces acting on the ball at the peak of the curve? Well, we have the weight of the ball, right? And it's going to be like a steel marble in this case. So the weight acts down. And we have a normal force, right, that the surface exerts on the ball perpendicular to the surface. And the way you do that is you draw a tangent line to the surface and it's perpendicular to that tangent line. So in this case, it'll be straight up. So there's a normal force like this. And you might even, if you're being really careful, there's also what's called a frictional force, and it's a rotational frictional force, but it's acting perpendicular. So it's not going to really affect our calculation. It's acting in this direction, depending on which way the ball is rolling. Okay, so what we want to do is we want to look at the sum of the forces just in the radial direction towards the center of that circle. So I'm going to call this direction right here. I'll do it in red here. This is like my plus R direction. You could say Y if you want. I'm just going to call it R for like radial. Okay, and actually on the other picture, I have the same situation, except here, the weight acts down, right, towards the center of the earth. The normal force also acts down. There could be a rotational frictional force. And again, I'm going to talk about, let's talk about just the radial direction towards the center of the circle. So this would be like plus R. Okay, so now we're going to apply Newton's second law. We're going to look at the sum of the forces in the radial direction, and that's got to equal the mass times the acceleration, but in this case, it's going to be the centripetal acceleration. Okay, so in the roller coaster track, let's see, I have W acting down. Remember I'm calling towards the center positive, so that's going to be positive W. Normal force is acting in the opposite direction, a negative direction in this case, so minus N. And that's got to equal M. And then for the centripetal acceleration, I'm going to write as V squared over R. And then in the second case, I have the weight acting down, so it's positive, plus the normal force is also positive, and that's got to equal mv squared over R. Okay. So here's the key point. And when you watch how I collected the data, so you should definitely watch the video on how I collected the data for this, the situation with the roller coaster track and the loop track. I have the position of the track set so that when the ball rolls over the top here, it's just ready to leave the surface at that instant at the top there. It's just ready to lose contact with the surface. And the same thing in this case, when it rolls underneath, it's just ready to fall here, just ready to leave the surface, so to lose contact. So if it's just ready to lose contact with the surface, then what variable can I set equal to 0? What variable can I get rid of? Well, the normal force, right? If it loses contact with the surface, then there's no force that the surface exerts on the ball. So I have this set up so in both cases, the normal force here is going to be 0. So this normal force is 0. Now I can write the weight as mg. So in this case, I'm going to get exactly the same equation. Right? It'll be the same equation in both cases. So notice what happens here. I can cancel the m's. And I want to solve for v. V is going to be called the critical speed, right? Or the critical velocity. It's the speed at which the ball is just ready to leave the surface. So to solve for v here, I'd have to multiply both sides by r. Right? And then take the square root. So you're going to find that v is equal to the square root of r times g. And this is what we're calling the critical speed, or you could also say critical velocity. And what the r refers to, if you're being careful here, is it's the path of the center of mass of the ball. It's that radius. So it would be this radius right here, the path of that center of mass of the ball. So if I were to measure this radius, that would be the one I want. So this is really r path. So the r here, I'm going to call r path. Okay, so that's the theoretical equation for the critical speed. It's simply going to be the square root of the radius, again, which means the radius of the path of the center mass of the ball, times g. In this case, by the way, this would be the path, right? Since it's rolling underneath. Okay, so let's go back to the handout. So again, I talked about the centripetal acceleration, right? We talked about the magnitude being v squared over r, or we could write it as omega squared r. Then we talked about centripetal force, right? Again, it's a force that's directed towards the center, and it's simply equal to ma, where the a is the centripetal acceleration. So it's either going to be mv squared over r or m omega squared r, depending on whether we want to use this linear velocity, right, which is also called the tangential velocity, or if we want to use the angular velocity or angular speed. We talked about the situation where the ball is rolling over the roller coaster track and then under the loop, and we derived the critical speed, right, when the ball is just ready to lose contact at that highest point, either just ready to jump off the roller coaster track or to fall off the loop. And that critical speed ends up being the square root of g times r, where the r here is the path of the center of mass of the ball. Okay, so for the first experiment, and again, this deals with this rotational apparatus, make sure you watch the short little video that I created where I describe how I actually collected the data. Basically, what you have going on here is you have this hanging object, and it's going to be rotated around in a circle. So this thing rotates around. Again, this will make more sense if you watch this video. And you're going to rotate it at a certain speed, a certain angular speed, so a certain omega, such that the hanging object hangs vertically. Okay, and then what keeps it going in a circle? So if you were to look from above, you would see its circular motion. It's going to be the tension in the string here. By the way, when you do that part, this string is not attached. So you have to kind of ignore this part. This is going to be the second step when we want to find the centripetal force experimental. So ignoring this piece right now. So it's just the hanging mass here. It's hanging from, hanging object here. It's hanging from a string. It has a weight. Those two forces are going to add to 0, right, when it's vertical. So the only force that's acting is going to be this force, the tension in the string that's pulling towards the center. And that's going to be the centripetal force that we're trying to calculate, okay, when it's rotating around. Okay, here's some information. The radius is 0.15 meters. So this post right here is 0.15 meters away from the center, or when the hanging object is hanging vertically, its center is exactly 0.15 meters away from the center. So that's the radius as it rotates around. I give you the mass of the hanging object. That's 0.2075. Remember, that's the thing that's being rotated, the hanging object. And then this you'll need later. The hanging mass here is that blue weight set, what we had to add to the hanger here, so that this whole thing is balanced and the hanging object is hanging vertically. And that ends up being 0.0700. Okay, so the first thing that you do, let me describe like where this comes from. So we want to calculate the centripetal force here, the tension in the string, both experimentally and theoretically. Experimentally, what we do is exactly this setup right here. We have another string on the left-hand side, which goes over a pulley and connects to this hanging mass. And then I put weights on the hanging mass such that this hanging object is completely vertical. It's just hanging vertically. So now we know that the tension on this side must equal the tension on this side. And I can easily calculate the tension on this side because the pulley here just redistributes that tension. So the tension pulling up, right, is the same as the tension pulling out. And I know if I look at this hanging mass, I have two forces. I have the tension pulling up and I have the weight pulling down, right? So it's going to be mg would be the weight. So since this is not accelerating in the vertical direction, that tension in the string must equal the weight of the hanging mass. So ultimately, the weight of the hanging mass is going to be your centripetal force here. It's sort of our estimate of the centripetal force experimentally. Okay, so all I did was I collected I put on, a particular mass there such that this was hanging vertically. So that's given in the table here. So it's 0.0700 kilograms. All right, later you're going to have to calculate the experimental centripetal force, but that's simply going to be this mass times g, right, times 9.8. Okay, now, again, you have to watch the video to see how I did all this. Now this string is taken off, and the hanging object will like swing up a little bit, but when you start it spinning, it'll go back down until it reaches the vertical position. And we know that because there's like a little orange indicator here that lines up with the bracket. So I know it's hanging exactly vertically. And what I'm measuring is what that omega is, what that angular speed is, such that this hangs vertically. So if you look at this table here, I did 10 trials, and this is the angular speed. So this is omega for each of those trials. And it's in radians per second. So 4.68 radians per second, 4.63 radians per second, and so on. Okay, so question 1, all I want you guys to do is to compute the average omega, so the average angular speed. Make sure you round to 2 places, right? That's the resolution of the instrument, is 0.01 radians per second. So round to 2 places. And then also calculate the percent experimental accuracy. So again, you have to find, right, we reviewed all this in lab 0. You have to find all the absolute deviations, how far each value is away from your average, then average them, make sure you round to 2 places. And then of course the accuracy is going to be the average absolute deviation divided by your average angular speed times 100. Once you have the information, so once you have omega here, Now you can compute the centripetal force theory. So this is our like theoretical value of that centripetal force. So remember, it's going to be m times the centripetal acceleration, which we're going to use the one involving omega. So it's m times r times omega squared. The m here is the thing being spun around. It's the mass of the hanging object, right? So the m here is the 0.2075. It's this thing that's being spun around. The r was given, right? The radius, 0.15, and then you can use your average omega for your omega here. Okay, so that will be the centripetal force theory. Okay, then I want you to estimate the percent experimental accuracy for the centripetal force theory. Well, remember, to do that, if you have an equation that involves multiplying several quantities together, then the rule is, if you want to find the percent experimental accuracy for this dependent variable, the centripetal force, you have to add these respective percent accuracies. And since omega is squared, you have to add it twice, right? So it would be the percent experimental accuracy for mass plus the accuracy for radius plus the accuracy of the omega, and you have to add that twice for omega. So for omega, we already have, right? You calculated it. So you have that value here. That's the percent experimental accuracy for omega. How do you find the percent experimental accuracy for mass and the radius? We're going to estimate it by using the resolution of the instrument, because we're only measuring the mass once and r once. So we're just going to estimate it. So remember, the scale, its resolution was 0.1 grams, which is 0.0001 kilograms. So to estimate the percent experimental accuracy for the mass, it's going to be 0.0001 divided by the mass of the hanging object, right? The 0.2075 times 100. So that'll be the accuracy for the mass. The accuracy for the radius is going to be 0.001, that's the accuracy of the instrument, divided by 0.15 times 100. And I have the final equation written here. If you want the accuracy for the centripetal force, it's the accuracy for the mass plus the accuracy for the radius, plus you have to add the accuracy for the omega twice, or you can just multiply by 2. Okay, so that'll be the percent experimental accuracy for your centripetal force theory. Okay, question 3. Compute the experimental value of the centripetal force, but that's just the weight of the hanging mass. And you have to be careful with these terminology, right? Hanging object is the one that's being spun around. Hanging mass is like blue mass set that you hung so that this balanced earlier. So if you compute the weight, we know the mass. If you multiply by 9.8, that'll be the weight of the hanging mass. That's going to be your experimental centripetal force. Okay, and that will go in here. This theory one, you can also write in here in this table. So question 4, I want you to compare these two. Hopefully they're fairly close by computing percent experimental error. Okay, make sure you show me all these calculations as well. Okay, question 5. How does the centripetal force vary with the angular speed for a constant radius of the circular path? I.e., is the relation linear, quadratic, cubic, inverse square, etc. So if you look at this equation, actually here, let me do this part on the iPad. Okay, so remember the formula for the centripetal force was m times r omega squared. And this question asked, how does the centripetal force depend on the angular speed if you have a constant radius? Okay, so the way to think about this, right? We know the mass is constant, right? The hanging object, that mass doesn't change. And if we're saying the radius is constant, then we know that these two variables multiplied together are just going to be another constant. Let me call it k. So the centripetal force is going to be some constant times omega squared. So another way of saying this is you can say the centripetal force is dependent on omega, right? It's a function of omega. So the question is, what type of function is that? Is that a linear function in terms of omega? Is it quadratic? Is it cubic? Is it inverse square, etc.? Okay, so I'll let you guys think about that. And then the next question was, assume that, so I'll start with the same formula here. Assume that now the angular speed is constant, how does the centripetal force depend on the radius? So the way to think about that now is if this, right, if that product is constant, I can think of this as it's a constant times r. So now it's really like a function of the radius. And what type of function is that? So if you guys remember, your pre-calculus or college algebra, what type of function is that? If it's like r, think of the exponent will tell you the answer, right? In this case, it's like a 1 here. Is it linear, quadratic, cubic, inverse square? What type of relationship is that? So that's all really that question, those two questions are asking. Okay, so next part B, this is the roller coaster track and the loop track part. So again, I recorded a short video showing how I collected the data. So you want to make sure you watch that video. That's really important to watch it. And basically the ball starts at the peg here. It's going to roll down, and I have it set up so it's just ready to leave the surface right at point P. And I have a photo gate set up there. So there's a photo gate right at point P. So in this first table, what I did was I collected the time it took the ball, so think of it as like the diameter of the ball, that steel ball, to pass through the photo gate, right, which was at point P. And these are the I did 10 trials. These are the 10 times I got. Okay, so question 7 is I want you to compute the average time that it took the ball to pass through the photo gate. Make sure you round to 4 decimal places. And then also compute the percent experimental accuracy for that time. Okay, then question 8, determine the average linear speed at position P. So determine the velocity at position P. And we're going to call that our experimental velocity. And we know that that is really our critical speed, right? Because it's set up so that the ball is just ready to leave the surface at point P. So how do we find that critical speed experimentally? Well, this is similar to what we did, if you guys remember way back. Actually, we did a couple of experiments like this, but in particular, the ball drop experiment, right? When we measured the acceleration due to gravity, we had to measure the velocity of the ball at photo gate A and the velocity at photo gate B. And to do that, we use the fact that the average velocity is displacement divided by time. And the displacement is really just the diameter of the ball, right? So same thing here. If we take the diameter of the ball divided by the time it takes to pass through the photo gate, that's going to be an estimate of our velocity at that point. And that is really our critical speed. It's our experimental critical speed. So the diameter of the ball is given. Remember, it's 1.90 centimeters, but in terms of meters, we want everything in SI units. It's 0.0190 meters divided by, you're just going to divide by your average time. And that will be your experimental critical speed. Okay, question 9. Now we want to calculate the critical speed theoretically, right? But to do that, remember, we need the radius of the path of the ball. So what I did was I took off that roller coaster track and the loop track, and I kind of sketched out the circular part of the track, and I measured the radius of that circle. So the radius of that circle is called, I call it R trace. Think of it, I traced out the track itself, assumed it was a circle, measured the radius, and that's R trace. But what we really want for our formula is our path, right? The path of the center of mass of the ball as it rolls over the surface. So how do I find R path if I know R trace? Well, it's almost equal to R trace. I have to add one little thing. What do I need to add? Well, I need to add the radius of the ball, right? It's the radius of the trace plus the radius of the ball. That will be R path, at least for the roller coaster when it's rolling on top. So R path for the roller coaster track is going to be R trace plus R ball. Okay, so I gave you the information in the table here so you can find R path. And then finally, question 10, now we can calculate the critical speed predicted or theoretical by using the equation. It's going to be the square root of g times R path. Right, and g, you can just use 9.8. Okay, now you want to compare. So the other part of question 10 is compare your predicted or theoretical critical speed to the experimental critical speed that you got from question 8 by computing the usual percent experimental error. And make sure you show me that calculation. Okay, part C, exact same thing, right? Same set of questions, except now we're dealing with a loop, right? So now it's rolling underneath. So again, I collected the time. I had a photo gate there that was installed. It was upside down now, the photo gate. And I collected the time it took the ball to pass through that photo gate for 10 trials. So these are my 10 values. So question 11 is compute the average time and compute the percent experimental accuracy. Question 12, determine the experimental critical speed, right? So the linear speed at position P, again, by using the diameter of the ball divided by the average time. So now this average time here in this table. Question 13, determine the radius of the path of the ball, but now it's rolling underneath, right? Because it's a loop. So now the R path is going to be the trace of the loop, the radius of the trace, right? When I sketched it out and I figured out the radius of that circle, minus the radius of the ball, right? That'll be our path. So compute that. And then question 14 is compute the predicted or theoretical critical speed by using that equation. And then compare again to the experimental critical speed that you found from question 12 here. And then how do you compare them? At the usual, we're going to compute the percent experimental error. And make sure you show me all these calculations, right? Show me the calculation for our path, show me the calculation for the critical speed predicted, and show me the calculation for the percent experimental error.